Hi, my name's Brett and I'm a Global Solutions Architect with Amazon Web Services. Today, we're going to be talking about advanced VPC connectivity patterns. These are questions that a lot of my customers come up with a lot of the time, and my colleagues also see the same sort of thing. So hopefully this will ring a bell and you'll get some value out of this. What are we going to talk about today? First of all, connecting your network to AWS. Second of all, what you do once you get in there, so how to route inside AWS. Third, how you share services in AWS. And fourth, the glue that kind of holds it all together, the DNS. So let's talk about connecting to AWS. A long time ago, we launched Direct Connect. You can still use this today, and customers have been using it for years. And this is how you would traditionally connect your on-premises network to your VPC in AWS. And it uses a construct called the private VIF. So VIF stands for Virtual Interface. Within the VPC, you create a virtual private gateway. From your on-premises network, you order a Direct Connect service, and that's pretty much it. It just works and it's all good. Now, this is important for later, but each private VIF that you create on that Direct Connect service has a single VLAN and has a single BGP session. We'll come back to that in a moment. Back in the day, customers used to first connect their on-premises network to AWS using a VPN. Why? Because it was very fast. You could set this up in minutes or hours. You didn't have to worry about provisioning any network. Customers also use VPN as a backup to their Direct Connect service. Works exactly the same way as Direct Connect, except that it's over the internet rather than a private network. We have a virtual private gateway, you have your on-premises network, and you build a tunnel. It's all in IPsec, it's all secure, it's very good. Just like with Direct Connect, you can use BGP routing or you can use static routing. And just like with Direct Connect, there is a single VPN per VPC. Now, if you're going to use VPN as a backup to your Direct Connect, I would strongly recommend that you use BGP because it gives you greater control over how routing happens in a failover environment. Now, the new and shiny, although it's not so new anymore, is Direct Connect Gateway. Direct Connect Gateway, on the skin of it, just looks exactly like Direct Connect. You build your virtual private gateway, you have your on-premises network, you order a Direct Connect, and in the middle, you stick a Direct Connect Gateway. Okay, so how is it different? Well, I'm glad you asked. If we look at it under the hood, from your on-premises network through Direct Connect to the Direct Connect Gateway, when you connect to VPC, we build a connection to the Direct Connect Gateway, and you get a VLAN and a BGP session to deliver all that information down. When you add another VPC, or a third VPC, or you subtract one, that VLAN and the BGP session stays the same. And this is the big difference between Direct Connect and using Direct Connect Gateway. You get one VLAN for all of the VPCs. You get a single BGP session, which means that all that happens when we add and remove VPCs is that the BGP table gets updated. And the other big addition here is that you can now be within one region or in multiple regions. So if you're using a Direct Connect Gateway in Sydney, for example, one of your VPCs could quite happily live in a different region, say in Virginia. So what actually happens under the skin on the network? And this is a topic that we discuss with customers all the time, so I thought I'd lay it all out here. So from your on-premises network into Direct Connect, somewhere close to your network, you'll have a router that's owned and operated by you. With Direct Connect, when you add a VPC, we stand up a VLAN and a BGP session. When you add a second VPC, there's another VLAN and another BGP session. And when you stand up a third, you get exactly the same way. Now, on your router, you could choose to transit all those VLANs directly through to your on-premises network, so you need to do some type of VRF routing there. Or if you wanted to, you could collapse it down to a single VLAN. That's completely up to you. With Direct Connect Gateway, it's much simpler. We bring that into the mix and you always have a single VLAN and a single BGP session. And it should be noted that this is the same with Transit Gateway, which I'm going to talk about in a little while. Now, some customers like to put a firewall on their on-premises network to guard them against potential external threats. And that's great. And depending on how you handle the VLANs, particularly in the Direct Connect scenario, you need to make sure that your firewall handles either a single or multiple VLANs. You might also be connecting to us via a partner-managed MPLS network. The partner might terminate the BGP session for you, and they might not. It's up to them what they do on their network. They may also decide in the direct connect case to transit all of those VLANs across to you, so you may need a layer 2 or a layer 3 service from them. You'll need to discuss that with them. So that handles private connectivity into AWS. What about public connectivity? We have an item called a public VIF. Why would you want to use one of those? Well, you might want to connect to AWS services not over the internet. Your internet link might be congested, it might offer too much variable latency, so too much jitter, or you might want to encrypt traffic to a VPC via a VPN, but not over the internet. But why wouldn't you do this? It requires another VLAN and another BGP session. You're probably going to want a firewall, you're probably going to want to use NAT. And you're not necessarily just going to have access to the services that you require. There's a lot more in there. Let me show you a diagram to explain. So you have our on-premises network and we have the AWS region. Normally you would connect to that via the internet. Fantastic. And you'd have access to all of these services. So things like S3, DynamoDB, basically any of our public API endpoints. By creating a direct connect public VIF, we can connect to all of those services, and we can connect that to your on-premises network. And just like with a private VIF, you're still going to need a router to do this to handle the VPN, the VLAN rather, and the BGP session. Now it should be noted that these are all public IPs. Okay, it is complete public IP address space in there. You're going to receive a number of routes from us, possibly in the thousands, and so that router needs to be sized for that. What that does mean is that you're going to have to do some sort of network address translation. Now, the network people out there will go like, well, that's not necessarily true. You know what, and you're right, but there are not very many customers who run public IPs inside their network now, so most people will be doing NAT to accomplish this. Now, if you have a VPC on the AWS side that has an internet gateway, it will have public IPs associated with it. These will be reachable via that link. So if that VPC is owned by you, you can just access it across that link rather than across the internet. Similarly, if there's a second VPC with an internet gateway, you can get that one too as well, but it might not be owned by you. That could be owned by another customer just with their standard elastic or public IPs associated with it. Similarly, if you or someone else has a VPC with a VPN attached to it, it has a public IP as well. So now you could run a VPN across that link, the public VIF, and into AWS, therefore encrypting traffic from your on-premises network into VPC-C in the diagram. Now the thing is, you might not want to have all of these services. Okay? You might want to protect yourself from them, and we would normally say you definitely have a firewall on your internet link. Let's put a firewall on this link as well. So we want to be very careful about what we allow in and out of that link. Bear in mind that this is a fairly sizable chunk of the internet that you're connecting to, and depending on what you do from a route filtering perspective, you're going to receive quite a number of routes from us. And speaking of route filtering, there's a couple of different ways in which you could do this. First of all, you can specify in communities which region you want to receive from us. We tag all those routes with communities. And secondly, we have a file that you can download called ipranges.json. It lists the IP ranges that are used by various AWS services. So you could say, I only want to receive the S3 routes, which then gives you a semi-private way of connecting across some MPLS circuit to AWS to use S3. And that's helpful if you're doing large-scale data migrations and you're trying to push a lot of data into AWS or trying to pull a lot of data out. Okay, once you're in AWS, what do we do next? Originally, we gave you the ability to peer VPCs. So this starts nice and simple. We have a nice VPC here, we have VPC-B, we have VPC-C, and we peer them together, and that's great. They can now all talk to each other. Notably, these VPCs cannot have overlapping IP address blocks. Okay? They have to all be unique, otherwise you just can't peer them together. Inside VPC-B, we have a route table. The route table says this is how to get to things. And in this case, it says destination for B is local, destination for A is via peering connection 1, and destination for C is via peering connection 2. Now, I want you to think about the route table here as kind of a lookup for a subnet. When a packet leaves an instance and comes onto the subnet, it looks up in the route table and says, where am I going to go? There can only be one route table for each subnet because that really makes sense, right? You can't look up in two places where the packet is going to go. But just bear in mind that concept, each subnet can have a unique route table if you want. Most VPCs have one, but you can have multiples. Here's the problem with VPC peering. Let's add another VPC. No, you know what? Let's add two. Let's peer them all together because we want them all to talk to each other. Now we have a problem. We have lots and lots of VPC peering connections. That's okay if it's static, right? But things change. And it also means that we have to go and update the routing table, not just in VPC B, which is the one we're looking at, but we have to update the routing table in every single VPC in order to make sure that everything talks. This can be quite painful. You can automate it, of course, and we encourage that. But at the same time, it's a lot of work. So how many peering connections do you need if you want to have a full mesh? So we have this simple formula. Let's imagine that we have 10 VPCs. Great. That's 45 peering connections. 10 VPCs doesn't sound like a lot, but 45 peering connections and 45 route table updates at least seems like a big thing. What happens if you have 100 VPCs? And believe me, lots of customers have more than that. That's 4,500 connections. This is bad for lots of reasons and not just for your administrative overhead. We have limits. You can only have 100 routes in a VPC route table. You can actually only have 125 peering connections. So clearly, this is not viable. So what are we going to do about this? Transit Gateway to the rescue. I want you to think about Transit Gateway as being a cloud scale router. Connect things to it, route, packets leave. Great. So in our example from before, let's take our 3 VPCs that we have. Let's add an on-premises network into the mix. And let's make sure they're all connected to Transit Gateway. So now we have these connections, 1, 2, 3, and 4. Now, our route table in VPC B looks a heck of a lot simpler. We have B again, which says this is all the local routes, and we have a default gateway that points to Transit Gateway. We basically say, hey, send everything to Transit Gateway and let it figure it out. So how does Transit Gateway know where to go? We also have a concept of a route table in Transit Gateway. And just like a VPC route table, the route table in Transit Gateway says when you receive a packet for this particular route, go down this particular attachment. So in this case, we go VPC A is available via attachment 1, VPC B via attachment 2, and so on. And that includes our on-premises network that can be connected via VPN or via Direct Connect Gateway, which is why we covered that earlier. And every time we attach more VPCs to this, we don't have to go in and update the route table for VPC B. Just like with VPC route tables, you can only assign a single Transit Gateway route table to a VPC. Because again, as the packet is leaving the VPC, we look it up in the route table, and that's where we decide to go. What's interesting is that you can have multiple route tables in Transit Gateway. So you could have a setup where route table 1 allows VPCs A and B to talk to each other, and route table 2 allows VPC C to talk to on-premises and back. But A and C, for example, can't talk to each other, and B cannot communicate with the on-premises network. Let's look at some of the terminology that you're going to need to use here. So an attachment is where we connect a VPC, a VPN, or Direct Connect into Transit Gateway. An association is the route table that is associated with that particular attachment. And propagation is where we automatically take the routes from a VPN, from a Direct Connect, or from a VPC and install it into the route table. So let's look at an example. Here's Transit Gateway, and this is what the route tables are going to look like. So VPC A, and let's actually use some real IP addresses, has 10.1.0.0/16. When we associate VPC A, that comes across connection X. We propagate the routes from VPC A across X into the route table, and therefore we've learnt how to get to 10.1.0.0/16, and it is via association X. VPC B is the same way. Everything is now from Y, and this is 10.2. And VPC 3 is 10.3. Our route table in VPC A is actually really, really simple. It basically says for everything, go to transit gateway, because there's only one link out, and that's cool. So very, very simple. And again, as I said earlier, when we add more VPCs, we don't have to change the route table in VPC A. Now, what about in VPC C? Let's say we put an internet gateway in there. We can't really have the default route pointing to transit gateway. That just won't make any sense. Instead, you'll have the default route pointing to your internet gateway. So how do we get to transit gateway? In this case, it's pretty easy. We just do a 10.0.0/8 route, and we push that to transit gateway. So it's pretty straightforward. Now, earlier, I said that routes can be automatically propagated into route tables. You can turn this on or off. Generally speaking, for any simple topology, you probably want it turned on so that when you associate a VPC with the transit gateway, those routes appear in the route table that is associated with that VPC. That's pretty easy. If you have any complex routing topologies, as in you want A to talk to B, but not to C, for example, you probably want to turn off automatic propagation of routes. You probably want to do that by manually entering the routes or by having some automation do that for you. So these are the advantages of transit gateway. I've already talked about many of these. You can create isolated sets of VPCs, and we have customers who really like to do this. They have production VPCs that can talk back to the on-premises network. You have dev and test VPCs that can talk amongst each other and back to on-premises, but the production and the dev and test networks can't talk to each other. And it's relatively simple to set up those sorts of topologies. One of the interesting things, as I mentioned before, about VPC peering is that you can't peer VPCs that have the same IP address block. In the transit gateway world, you can attach VPCs to transit gateway that have the same or overlapping IP address blocks. However, transit gateway is not magic routing or anything like that. They still cannot talk to each other via transit gateway. You would need to route that traffic through another VPC that does some static or double-sided NAT in order for those two VPCs to talk to each other. So transit gateway is not magic, but it does allow you to set up those topologies if you like. Okay, now that we've done that, let's talk about sharing services in AWS. So what we want to do is we want to reach resources and applications and services that are in another VPC or on premises. Okay, but how do we do that without exposing data to the internet? How do we do it without peering or routing? The answer is PrivateLink. And the way PrivateLink works is we can take a service that's presented in another VPC and insert it into a VPC that is, say, a consumer VPC, and it just appears as a local IP. The great thing about this, we don't actually care whether the services VPC and the consumer VPC have overlapping IP address. We just do some double-sided NAT for you and it's all magic. Okay, so that's great. These VPCs can also be in different accounts, which is great if you're setting up a multi-account environment where some people are operating services and other people are acting as consumers of those accounts. So this is our simple diagram. On the right, we have our service provider. They're in our provider VPC. On the left, we have our service consumer, and we take PrivateLink and we use it to expose the network load balancer in the provider VPC into an interface VPC endpoint in the consumer VPC. This is just an elastic network interface and ENI. We use this at AWS to present AWS public APIs to you inside your VPC. So here we have an instance that's reaching out to a VPC endpoint. We use PrivateLink to basically hide the public IP addresses of the AWS service from you. What this means is that instances in that VPC do not need an internet gateway or any other sort of public internet access in order to access AWS services that are presented via PrivateLink. This is ideal for SaaS providers. They can have their own VPC in their own account. They can present services into customers' accounts. And again, we don't have to worry about whether the IP addresses are overlapping. All they need to do is set up a network load balancer, present that via PrivateLink, and we deliver traffic into the instances that are connected to and registered with the network load balancer. Now, something has to be said here that because a VPC endpoint appears as an elastic network interface, you, as the provider, need to make sure that you're presenting ENIs into the right availability zones for your consumers. So we encourage you to be very, very highly available here and put ENIs into every single availability zone. From your perspective, when you launch PrivateLink, you simply choose the subnets into which you want to present an ENI. It turns out that VPC endpoints are reachable from on-premises, either via Direct Connect or via VPN. So what this means is that your on-premises servers can reach through Direct Connect to the VPC endpoint and then onwards into the service provider VPN. So it really is a great hybrid solution. One of the other tricks with Network Load Balancer is that you can use NLB to load balance across on-premises servers. Because you're using an NLB to do this, you can now present on-premises services via the NLB and PrivateLink to VPC consumers. From a VPC perspective, they think the service is just a local interface. It looks like it's in AWS, but behind the NLB, we're actually sending traffic across on-premises, again via Direct Connect or via VPN. In this example, we have a consumer VPC in one region and provider VPCs in a different region. We can use cross-region VPC peering to connect two VPCs together and then allow the VPC, in this case in US East 1, to connect to something in AP Southeast 2 to consume that service. Now, normally we don't encourage people to create inter-region dependencies. We don't like it, and you shouldn't either. However, we appreciate there are customers that have applications that simply can't be hosted in more than one region. Again, you can use some PrivateLink magic here to load balance across instances that are in a different region. So this is a slightly different pattern for doing this. Again, I would encourage you not to create inter-region dependencies if you don't have to. One of the common patterns we see is the creation of a shared services VPC. If you have lots and lots of services VPCs and lots of private links and many consumer VPCs, or many things on premises that want to consume stuff inside AWS, you might find that creating lots and lots of VPC endpoints is kind of hard work. Rather than do that, create your VPC endpoints in a single shared services VPC and consume them all there just once. So those endpoints, as we mentioned earlier, are available via Direct Connect or via VPN. And if you have other VPCs that want to consume those services, you could do that via Transit Gateway as well. So we always encourage you to use at least 2 availability zones. Please consider using DNS names to look up things, and we're going to talk about that in a moment. Okay, and make sure that if you're using NLB to present your resources across, say, 3 availability zones, that you don't try and cross the availability zones on the way through to the consumer VPC. And lastly, please avoid building inter-region dependencies if at all possible. Okay, let's move on to DNS. Route 53 has been available in AWS for a long time, and DNS inside of VPC had a bunch of different names depending on who you were talking to or where it was in the documentation. So you know what, we gave it an official name, and here it is, the Amazon Route 53 Resolver. What does the Route 53 Resolver do, the one that's based in the VPC? Basically, it's a recursive DNS lookup. It's available on the +2 IP address of your VPC. So if your VPC addresses start at 0, then this will be at 2. If your VPC addresses start at, say, 128, it will be at 130. And there's built-in redundancy. It's all hosted within the hypervisor. The challenge from our customers was they wanted to look up things inside a VPC from outside, and that was pretty hard. They had to go and build their own infrastructure to do that. The Route 53 Resolver fixes all of this. Across the Route 53 Resolver, when you enable it, you can look up private Route 53 zones, you can look up the VPC DNS, and you can continue to look up public DNS records. So here's an example. There are 2 types of resolver endpoints. There's an inbound and an outbound, and they do pretty much what you would expect. The inbound endpoint is used for things outside the VPC, pretty much stuff that's on premises, to look up things inside the VPC. So you create an inbound Route 53 resolver, you point your on-premises DNS at it, and then it can look up things inside the VPC. An outbound endpoint does exactly the opposite. It appears as an IP address inside the VPC, and it means that services inside the VPC can look things up and are then forwarded to your corporate DNS server. That can be via VPN or Direct Connect, we don't mind. And again, there's built-in redundancy. Okay, and the one thing you've got to be aware of again, because this is kind of delivered via PrivateLink, is that one endpoint equals multiple ENIs in your VPC. There is a limit of 10,000 queries per second. That sounds like a lot, but if you've got a large amount of infrastructure, just watch out for that. And we do have a CloudWatch metric that will help you with that. When you configure your Route 53 resolver, there are two types of rules. There are forwarding rules and system rules. The forwarding rules say, for this particular zone, I want you to send it to this remote DNS resolver. And we heavily encourage you to put static IP addresses on those DNS resolvers. Please don't have them move around the network. System rules are created automatically inside VPCs so that when you send something to the resolver, it can find DNS names and resolve them inside Route 53 itself. So here's a nice complicated pattern. We have a corporate DNS server that talks to an inbound and an outbound resolver endpoint, and then we share that across multiple VPCs. What this means is that your on-premises network can now reach into all of those VPCs and find things. And those VPCs can also resolve names and IP addresses inside the corporate DNS server. So best practices. If you're operating inside a VPC, use the .2 resolver. Okay? It's cheap, it's there, it's simple, and it doesn't have that 10,000 query per second limit. Always put endpoint ENIs in multiple availability zones. Again, this is the same rule as with PrivateLink. Use conditional forwarding for on-premises, which means only send the queries on-premises that have to go there. And avoid using A records when you're referencing ENIs inside a VPC. Always use an alias or a CNAME record because you just don't know when those IPs are going to change. Okay. And avoid pointing your outbound endpoints at inbound endpoints. Yes, you can do that. That's probably not very smart. Okay. And again, look at the CloudWatch alarms on those resolver endpoints to find out when you're approaching those limits. And finally, and I mentioned this before, maintain fixed IP addresses for your outbound resolver targets. Okay, so some key takeaways from this presentation. PrivateLink endpoints are highly available. Put them in multiple availability zones. Route 53 is highly available and fault tolerant, and you should definitely use the Route 53 resolver if you have challenges between on-premises and inside your VPC looking up names. And using PrivateLink and Route 53, you can create some very, very interesting data flows between clients and servers that are either in AWS or on-premises. Back to the beginning, Direct Connect Gateway makes adding and removing VPCs to your network pretty easy. Public VIFs are there, but be aware of what you're getting into. It is definitely a public connection. And Transit Gateway, for most use cases, is definitely way better than VPC peering. Now, I snuck a bonus slide in for you. Lots of customers are interested in Outposts. If you don't know what Outposts is, it's basically where you get a rack of equipment from us, or several racks if you like, and put it in your data center. It is the same equipment that we use in our facilities, delivered to you. Why would you do that? You might want to run an application locally, you might have latency sensitive applications, or you might want to have something where cutting the network to it and back to the region is a no-no. So you need local survivability. This is an eye chart, and I apologize, I am not going to read all of these things to you. Two important things. One, you can't use the outpost as traffic transit to a region. So you cannot bring traffic into the outpost and then onto the region. You're still going to need your Direct Connect or your VPN service. The outpost can access local networks via a thing called a local gateway, and it acts just like an internet gateway. Otherwise, the outpost is basically just a stretched VPC from the region out to your premises. Come talk to us about it later. Finally, thank you. I hope this has been of value. Have a great day.